What is your scientific background, and what led you into this work that enabled you to be a part of this extremely exciting discovery?
So I call myself a planetary photochemist. What that means is I'm interested in the interaction of high energy radiation, like ultraviolet radiation, with molecules. And I'm particularly interested in understanding how this interaction affects life, in particular the ability of planets to host life and our ability to detect it on those planets as well. So that's kind of my broad research area.
So this was at MIT that you were doing this research that was a part of this discovery?
That's correct. I got involved with this particular work at MIT as part of an existing initiative at that institution.
Awesome. And who was the leader at MIT of this particular work?
I got involved with this project through the leadership of Professor Sarah Seeger as part of her All Small Molecules program, which attempts to evaluate a wide range of gases as potential putative biosignatures. My role was primarily to contribute to the photochemical aspects of this work, because that's my personal focus area.
What does that mean, photochemical, exactly? How did that contribute to this discovery?
There's a few different ways of answering this question, but stepping back a little bit, essentially what that means is I tried to understand what the atmospheres of different rocky planets are made up of, and what are the factors that control and affect that. So the idea is, let's suppose you had a source of some gas, like let's say methane or phosphine or something like that on some rocky planet. What I try to do is help calculate how that gas builds up, to what concentrations it can accumulate in the atmosphere of a rocky planet, and how that varies with height, how that varies with altitude. So overall, you can think of it as trying to understand, make predictions, and make models of what are the atmospheres of different rocky planets like Earth, Mars, Venus, and planets orbiting other stars made up of.
So why is phosphine gas particularly interesting?
So phosphine gas is a little bit of a weird gas, and it's not interesting depending on who you talk to, it's not interesting in all environments. It's a very simple molecule in some sense. It consists of a phosphorus atom, one of those fundamental elements, connected to 3 hydrogens. Mm-hmm. And it's not a very complicated molecule. It's not like DNA or RNA or anything like that. It's very simple, only 4 atoms. Mm-hmm. And there's some places in the universe you expect to find it very commonly. For example, inside of gas giants, you find a lot of phosphine in the deep, hot interiors of gas giants.
Oh.
And the fundamental reason for that, by gas giants, I mean planets like Jupiter and Saturn, which are giant planets in our solar system, the biggest planets in our solar system, and they're made up almost entirely of hydrogen. They have a ton of hydrogen in them. Because they have a lot of hydrogen there, and in the deep, hot interiors of those planets, if you stick a phosphorus atom there, one of those P's, it tends to bond to those hydrogens. And so it makes phosphine. Mm-hmm. And that's the source of the phosphine we see in the atmospheres of those planets. And it's perfectly normal that we completely understand it. It's completely expected.
So that we see it all the time in the gassy planets, and it doesn't mean that there's life there.
Absolutely not. Yeah, we know exactly what's causing it, completely abiotic, very well understood thermodynamic.
Mm-hmm.
Okay, awesome. So yeah, what makes it different in Venus?
So Venus is a very different planet from Jupiter and Saturn. The biggest difference is that it has very little hydrogen. Its atmosphere instead has, if you were trying to break it down into elements, it really has a lot of oxygen. That oxygen is not free oxygen. It's not O2, the kind of oxygen that you and I and all the other animals here on Earth breathe. It's bonded to other atoms. So what that means is that, for example, carbon on Venus tends to be present primarily in the form of CO2. That's carbon bonded to 2 oxygens. Similarly, sulfur on Venus similarly tends to be found in the form of SO2 and its derivatives, sulfuric acid, as opposed to bonded to hydrogens. Similarly, you expect to find phosphorus on Venus bonded to oxygens, not to hydrogens. So that's the weird thing about Venus, is finding a significant amount of phosphorus bonded to those 3 hydrogens instead of oxygens. Now, I want to emphasize that had we even detected phosphate species, that would have been a little wild. We hadn't really considered those in our models of Venus before, although in retrospect, we should have. But the phosphine was a little bit exceptional, because even once we went back and looked at the data from the old Soviet landers and so forth, we couldn't really figure out a way for it to be there at high concentrations. We tried to work out, and 20 parts per billion, which is what we detected at, doesn't sound like a lot. But if you look at how unlikely it is to make that phosphorus in Venus's atmosphere, according to the mechanisms that we currently know about,
Right.
and I want to emphasize the depths of our ignorance here.
Right.
That's the weird part. We weren't able to figure out a mechanism yet that can explain the presence of that phosphine gas in the atmosphere of Venus.
Oh, wow. That's really cool.
So what does that mean then?
What that means is that we are very ignorant people. And so what it means is we found something weird and we'd like to understand what's going on. In a sense, this is nothing new. Science is all about finding things that are weird and don't conform to expectations, and then trying to figure out how they're there. And then once you understand it, everyone is like, oh, of course, this is how it should always have been there. I don't understand how those people that came before us could have been so foolish as to never not expect it to be there. Like, computers are super easy to make. I can't figure out, all you need to do is like take some sand and melt it down and do things to the silicon. I can't understand why our ancestors didn't invent them 1,000 years ago.
Right.
So there's a similar thing going on with phosphine over here. We found something weird. We didn't expect it to be there expected to be there. We've iterated through the mechanisms we know to look at, like volcanism and lightning and so on and so forth. And those don't seem like very good fits. You have to assume really weird things about the planet in order for those to work. So all of them seem to us like the most conservative explanations right now seems to be to rule them out. So we have two options we're left with. The one that I think is most strongly worth focusing on is that there's something going on either with Venus or with the photochemistry, the chemical reactions regarding phosphine that we simply don't understand. And there's a lot of ignorance there. We know very little about the bottom atmosphere of Venus. It's because it's violently hostile to space probes. It tends to melt them. This is bad for getting data.
Right.
Yeah.
So there's a ton of unknowns about the lower atmosphere of Venus. And there's actually a lot we don't know about the chemistry of phosphine. That's because phosphine, to a life like ours, oxygen-breathing life, is violently toxic. OSHA frowns upon doing experiments with it unless you have a lot of very expensive equipment and a lot of safety precautions. So there really hasn't been a good reason to measure it or characterize those before. There is one other mechanism for phosphine generation that we know of. And we hesitate to reach for it because it's kind of an extremal hypothesis, which is that we do know that here on Earth, phosphine production is associated with life. So, and this is interesting in the context of Venus in the sense that going back many decades to the foundational papers by Sagan and Morowitz, it has been proposed that the cloud decks of Venus are in some remote sense habitable, in the sense that you have liquid water there and the temperatures and pressures aren't too extreme. And we do happen to detect the phosphine at an altitude that is roughly coincident with that, which means that does not mean we've detected life by any means, or even that we've detected convincing evidence of life. It means that life is not yet ruled out.